Have you ever seen something that someone called a digital twin that, when you look at it closely, it's really just a 3D model? Yeah, I've seen that too. And if you're in a position to fund or support these projects, you deserve to understand what actually makes them work. I am going to break down why so many digital twins fall short, and what separates these flashy demos from systems that actually support real decisions. I have spent years designing and advising on complex digital systems across public health, sustainability, national intelligence, and many other domains. And I have seen strong ideas struggle once they collide with messy real-world conditions. The good news is that these failures are not random. There is a pattern to them, and a clear path to building systems that are more resilient and more useful. We will look at why digital twins often don't meet expectations, what effective architectures really look like, and how to move from static visuals to systems that can adapt as the real world changes. By the end of this video, you should have a much clearer sense of what a digital twin should be and how to recognize whether one is actually built to work. Let's start with the promise. At their core, digital twins are meant to be living, evolving digital counterparts to physical systems. So that could be a factory floor, a transportation network, a hospital system, or even an entire city. They monitor conditions in real time or near real time, simulate possible future scenarios, and provide decision makers with the information they need to act earlier and with greater confidence. The idea itself is not new. NASA used early forms of digital twins during the Apollo missions to simulate spacecraft systems from Earth. What has changed, though, is the scale. Today, we have access to far more sensors, data, and computing power than ever before. As a result, the use cases have expanded rapidly. Cities want digital twins to manage traffic, energy usage. Hospitals want them for logistics and outbreak response. Utility companies, they want them to anticipate failures before they happen. The potential is enormous. And in public health, especially, where timing and coordination can literally save lives, a well-designed digital twin can help governments plan more effectively, allocate resources more intelligently, and detect early warning signals before a crisis escalates. Based on my years of work across public health, urban systems, and national intelligence, and large-scale data platforms, the future of digital twins goes well beyond the current implementations. Advances in AI now allow us to extract, summarize, predict, and fuse data much faster than before. That makes continuously updated systems far more realistic. In the past, keeping digital twins up to date was a massive effort and often led to, one-off applications. At the same time, the rapid growth of AI, especially generative AI and now agentic AI, is increasing demand for richer data beyond just text and images. Over time, this will drive the deployment of more sensors, the development of new sensors, new types that capture environmental, infrastructure, and human signals with greater precision. And we will develop new sensors that we can't even imagine yet. Together, better data and better AI open the door to digital twins that help people and machines work together to understand complexity and make better decisions. But this is also where the gap begins to show. Despite the promise, most digital twins, they don't fail because the whole idea is flawed. They fail because the underlying systems were never designed to support this level of intelligence. Instead of dynamic tools that evolve with the world, many end up as frozen, oversized dashboards that are impressive at launch and then quietly abandoned afterward. And this is not just disappointing. It is a massive missed opportunity. So let us talk about why so many of these projects do not make it. The first issue is definitional, or perhaps simple marketing. A lot of what's called a digital twin isn't one, plain and simple. It is a visually appealing 3D model stitched together from drone or satellite imagery. It may look impressive, but if it does not evolve, connect to live systems, or support simulation and response, then it's not a digital twin. It is a static representation. The second issue is architecture. A real digital twin depends on continuous, consistent, and reliable data streams. In practice, many systems are built on disconnected databases, incompatible formats, and legacy interfaces that were never meant to work together. You cannot create a living system on top of broken data plumbing. Third, there is the integration complexity. Connecting a few systems in a controlled pilot or an academic study, that's one thing. Scaling across departments, agencies, or regions is something else entirely. Even new connections add fragility. If the system is too brittle, it breaks before it even delivers value. Fourth, there is the problem of unclear return of investment, especially in public health. Initiatives start with broad goals, such as improved awareness or better decision-making. But public health leaders are accountable for outcomes under tight budgets and real human consequences. Without measurable values, such as early outbreak detection, better surge planning, improved resource allocation, or faster emergency response, long-term support would otherwise fade quickly. And finally, there's the illusion of completion. Oh, we're done. Teams build a front end, launch a platform, and assume the work is done. But the digital twin is not a product you finish. It is a system that has to evolve as data sources change and new questions emerge. The bottom line is simple. Building digital twins correctly is hard. And unless they're designed to survive real-world complexity, they rarely last beyond the demo stage. Research backs this up. A recent review of digital twin deployments found that many fail due to poor data quality, inconsistent inputs, and integration bottlenecks. Without clean, connected, and continuously refreshed data, even sophisticated models quickly lose value. If these challenges sound familiar, you're not alone. One thing you learn very quickly when you move from pilots to real deployments is that the real world does not cooperate. Systems that look solid in controlled settings often crack when exposed to real conditions. In public health, complexity shows up as shifting population behavior, incomplete reporting, and environmental factors that can change by the hour. In cities, it shows up as aging infrastructure, political timelines, funding cycles, and citizen expectations that are constantly evolving. I have seen many data-driven platforms and decision support systems where early pilots looked promising. The user interfaces were clean, the workflows were clear, and there was genuine enthusiasm. But once those systems had to connect to live data, integrate external sources, or scale across regions, problems emerged. Data strips stalled, interfaces timed out, queries lagged. Different parts of the system drift out of sync. These issues were rarely, a people problem. It was almost always a design problem. The system had not been built with real-world complexity in mind. A simple example is one organization labeling a field patient space ID, while the other uses something like ID_patient. These small changes, they build up over time. Sensors drift, networks fail, weather disrupts data collection. In short, things go wrong. Another common issue is over-specialization. One team focuses on the interface, another on sensors, another on analytics, but no one is responsible for, the system as a whole. The result is a collection of capable components that never quite function as a cohesive system. And then there is maintenance. Complex digital systems require ongoing care. Without clear ownership and responsibility for keeping them aligned with reality, even well-designed systems slowly turn into something that looks impressive, but no longer reflects how the world actually works. These are hard problems, and there is no shortcut around them, but they are solvable. especially when teams are honest about what they are building and designed for scale and messiness from the very beginning. And that leads to the most crucial question. Not whether a digital twin looks impressive in a demo, but whether its underlying architecture was designed to survive real-world complexity. Messy data, inconsistent systems, human behavior, and constant change are the norm. If a system cannot stay coherent as the world turns, it will not deliver value for long. So a real challenge becomes architectural. How do you design a system that can absorb this complexity and keep working over time? So, what does it take to build a digital twin that works? Across research and real-world implementations, a consistent pattern emerges. Successful systems share a small number of core components. When these are missing or weak, the system struggles. First, real-time data integration. Continuously updated data is the heart of any digital twin. Data needs to flow continuously from sensors, remote feeds, legacy systems, and modern platforms. It must be harmonized, time-stamped, and especially trustworthy. The data also requires strong permissions and data governance, so that different users see the appropriate data for them, and that someone is accountable for the quality and ownership of the sources. Second, memory of what has happened before and what is happening now. A digital twin needs history. Storing past data allows teams to understand how a system evolved, detect trends, and test scenarios. In public health, understanding timelines can change how interventions are planned and how they are evaluated. Third, the ability to connect and communicate across systems. A digital twin cannot live in isolation. It must pull from or push to multiple sources, such as geographic data, health records, environmental sensors, and operational systems. This data fusion requires modular integration, not fragile one-off connections that break as soon as something changes. Fourth is a clear connection between the system and the people using it. A digital twin should not just track conditions. It must support the back and forth response to humans. And that might mean alerting officials to emergency risks, recommending actions, or triggering predefined response protocols. What matters is that information moves quickly from data to people who can act. Fifth is grounding in real-world location. A digital twin must connect its data and insights to physical locations and perform precise data fusion at each location. I've done a lot of work throughout my career with relational database management systems and SQL. And in databases and SQL, we're always thinking about joins. We got inner joins, outer joins, left joins, right joins, and even full joins. These are all ways to fuse data. And location serves as a natural SQL join. When you have data with location, and often the time component is critical, it is an effective way to fuse diverse data sets to solve complex challenges. Location adds context. It enables pattern detection, prioritization, and targeted action. And of all the areas I've worked in, mapping is perhaps where my experience is deepest. And I can say with confidence that there are many ways to introduce serious errors if it is done poorly. Precise digital mapping matters because even small mistakes can lead to incorrect conclusions and decisions. But correct handling of location opens up a world of possibilities. Together, these components transform a static dashboard into a digital system that can support real decisions. But getting this right requires real effort. Strong data engineering, transparent governance, and of course, close collaboration between technical teams and domain experts. All of these are not optional, they're requirements. The good news is that AI is helping make this work more achievable than it used to be. Beyond structuring organized data and helping with integration, AI can detect data quality issues, identify inconsistencies, and flag anomalies that are difficult for humans to catch at scale. I am currently working on a project in Abu Dhabi in the UAE where AI is integral in data validation across diverse sources. It can learn typical system behavior, highlight when something looks off, and support forecasting and scenario analysis. Overall, these capabilities help turn raw data into structured information and usable knowledge that supports better decisions. Now, let us address a common trap that's confusing a digital twin with a good-looking dashboard or a 2.5D or 3D model. It happens all the time. Funding is secured, the project launches, and everyone's excited to build a digital twin. What gets delivered is a polished interface, a sleek 3D scene, a few charts pulling in historical data. It looks great in a demo, and it checks a box in a report. But it's not a live digital twin. Real digital twins are more than visual layers. They're systems of intelligence. They stay in sync with reality and support decisions as conditions change. A dashboard tells you what happened, but a digital twin helps you understand what is happening now, what might happen next, and what are the options you have. Where many teams go wrong is treating the interface as the goal, the end goal. In reality, the interface is just the surface. What matters is the system underneath. Think of a working digital twin like a living nervous system. Data is the sensory inputs, AI is the brain, the operational responses that carry decisions into the real world, those are the muscles. But if one part of the system breaks, the system collapses. When everything works together, the system can perceive, reason, and respond. And that is why it is essential to invest in data architecture before worrying about the visuals. Interoperability, scalability, and automation matter more than the outside polish. So if you're in a position to support or build these systems, resist the pressure, resist the temptation to start with appearance. Start with the substance. Then design the interface to reflect real intelligence, not to decorate it. If these challenges resonate with you, feel free to reach out. I have spent years working across scientific research, business applications, and public sector systems, contributing to technical and organizational foundations on which these systems rely. A central part of my work is translating complex, imperfect data into tools that real end users can depend on in close collaboration with domain experts who understand operational realities. To make this more concrete, consider an example from my recent work. I've been involved in this environmental-focused project in Abu Dhabi, aimed at improving how complex operational data is validated, analyzed, and used for planning and forecasting. The work consists of using AI to flag inconsistencies, explore future scenarios, and support reasoning across systems with many moving parts. And while it's not a digital twin in the formal sense, it addresses many of these same challenges, including data quality, integration, coordination, and the need for systems that can evolve as conditions change. I am very much enjoying helping turn their vision into reality. And over time, systems like this can grow into something even more powerful by connecting data across planning, operations, and environmental impact. They can help teams test interventions before deploying them, surface some of the issues earlier, and coordinate across organizations. And this kind of systems-level reasoning is what digital twins are ultimately meant to enable when built on solid architecture and a clear purpose. One of the most critical shifts in recent years is how AI is changing what is possible when building and maintaining digital twins. Not long ago, creating these systems required enormous manual effort. Data engineers spent months untangling siloed datasets. Analysts worked through endless format mismatches. Each new integration felt fragile, but that is changing. Today, AI tools can dramatically accelerate this work. Large language models can help us organize metadata and structured unorganized datasets. Computer vision can extract meaningful features from satellite, aerial, and drone imagery, as well as field photos. So instead of that purely visual 3D scene, The system can understand the actual objects and features in the images. AI tools can also support simulation and monitoring. Forecasting tools can predict future scenarios, detect anomalies, which are things or events that are out of place, and then flag them in near real time. But of course, AI is not a shortcut around poor design. It cannot fix weak architecture on its own. But when combined with experienced teams and solid infrastructure, it becomes a multiplier. It reduces manual workload, improves consistency, and speeds up the insight generation. It also enables new capabilities. AI can illuminate patterns that are hard to see otherwise, such as seasonal effects, spatial clusters, and operational bottlenecks. In public health, this can mean detecting early signs of outbreaks by tracking changes in movement, environmental conditions, or system strain before traditional reporting systems catch up. In the last decade, I've seen many of these AI use cases go from research challenges to solved problems. The key is to use AI as a partner in the system, not as a quick fix. It should strengthen core functions such as data integration, analysis, and decision support, rather than simply being added to generate disconnected predictions. With the proper foundation, the right team, and a clear purpose, building effective digital twins is becoming more achievable than ever. Let us assume you have built a solid digital twin. It is accurate, responsive, and already delivering value. Now, the real challenge is keeping it that way. Digital twins are not one-time projects. They require ongoing care, just as the systems they represent do. Without attention, even well-designed systems decay. Data and model predictions drift, integrations break, the relevance fades. Sustainability has to be designed from the start. First, data governance. There must be clear data ownership. Someone needs to be responsible for data documentation, pipelines, validation, and alignment with operations. Second, alignment with tangible goals. A digital twin should solve a mission-critical problem and not exist as a technical showcase. Tying it to concrete outcomes helps secure long-term support. Third, flexibility. Systems evolve. A digital twin must be modular enough to adapt without being rebuilt from scratch. Fourth, continuous learning and adjustment. The most effective systems improve over time. They take in new data, update analyses, and adapt as conditions change. These automated adjustments require transparent processes for review, refinement, and accountability. When done well, a digital twin becomes part of how an organization thinks. It supports long-term planning, coordination, and decision-making. We can see this in some of the well-known examples. One of the most cited is the digital twin of Singapore, often called Virtual Singapore. It integrates detailed spatial data with real-time information from infrastructure and environmental systems to support national-level planning and simulation. Its value comes not from visualization alone, but sustained integration, governance, and use in real decision processes. Let us bring this all together. Digital twins are not just 3D models or dashboards. They are dynamic systems designed to reflect reality, anticipate change, and support action. Most fail because they are built on fragile data, siloed systems, or have unclear goals. The ones that succeed, they share common traits. They have strong architecture. They have real-time data integration. They have spatial grounding and the ability to evolve as conditions change. With advances in AI and data infrastructure, building these systems is more achievable than ever before, if approached with the right mindset. From health and infrastructure to environmental and urban systems, when a digital twin works, it stops being just a technical tool. It becomes a partner in decision-making. So whether you're building one, funding one, evaluating one, or using one, ask the hard questions. Does it stay in sync with reality? Can it scale? does it actually help people act? In a future video, I will explore geospatial foundation models, what they get right, where they fall short, and how they can be fine-tuned for real-world missions, including public health. These models are another class of technology that can accelerate digital twin development and especially help keep systems up to date by automating data integration, pattern recognition, and semantic understanding across large, evolving spatial and temporal datasets. If this video helped clarify what a real digital twin looks like, consider sharing it with someone who might benefit. If we build these systems with good data, a clear purpose, and collaboration, digital twins can do more than save money. They can help create more resilient, informed, and responsive systems. Thank you so much.